Jai Hind everyone. I, Dr. Prashant Tripath, going to discuss a topic related to wireless and mobile communication, and the topic is spread spectrum communication. This topic is related to subject wireless and mobile communication, and this subject is taught in 7th semester of ECE student. In this topic, we will discuss about spread spectrum modulation, pseudo noise code and its property, code generation mechanism, direct sequence spread spectrum, frequency hop spread spectrum system, time hopping and hybrid spread spectrum system. So, in this lecture, we will cover these topics in detail. First of all, when we talk about spread spectrum, then the idea comes into our mind, what is spread spectrum? So, spread spectrum was initially introduced to save our channel from our signal from enemies. Its purpose was to provide a secure transmission in military environment, and its invention was aimed for military application. But due to its advantageous feature, this modulation scheme is also used in the commercial applications. So, we will see now what is spread spectrum modulation. In spread spectrum modulation, the information is transmitted at a larger bandwidth, which is far above than the required minimum bandwidth, which is required to transmit the desired information. In this method, the signal generated within a particular bandwidth is deliberately spread in frequency domain, and the spreaded resultant signal is transmitted over a wider bandwidth. To obtain this goal, the spread spectrum modulation techniques basically add some redundancies into the original spectrum. For example, if the required bandwidth for each station or each source is B, the spread spectrum modulation technique expand this bandwidth to BSS, and this bandwidth BSS is far greater than the required minimum bandwidth, that is B. The expanded bandwidth allows the source to wrap its message in a protective envelope for more secure transmission. As I have told you that initially it was developed for military applications because they have ability to combat jamming and interception, and they have different other advantages like multipath mitigation, flexibility, robustness. They become attractive choice for the civilian applications. The spread spectrum modulation technique is simple. Generation of spread spectrum modulation technique is quite simple. In this modulation scheme, we expand the bandwidth of original information by just using the spreading codes, which is shown in this figure. As we can see in this figure, this is the required minimum bandwidth which we have to transmit using spread spectrum modulation technique. In spreading process, we just use this desired signal in association with the spreading code, and the resultant is the spreaded signal which we transmit in our applications. To spreading the bandwidth of original information, we use spreading code, which is basically looks like a random sequence, but they are actually a pattern. The most popular and common spreading code is PN sequence, which is popularly known as pseudo-noise sequence. The term pseudo-noise sequence arises because it looks like noise but it has a regular pattern. The PN sequence is binary periodic sequence with a noise-like waveform, and it is basically generated with the help of feedback shift register and logic circuit. As we can see in this figure, it contains a shift register which is made from flip-flops and a logic circuit. In this logic circuit, we perform different kind of logical operation. Usually, we use modulo 2 addition for the generation of PN sequence. This feedback shift register output is fed into the logic circuit, and all the flip-flops in the shift register are governed by a single clock pulses, as we can see from this figure. Each time when we trigger the clock, the logic circuit compute a Boolean expression, a logical expression, and the output of this logical expression is fed into the first flip-flop. When we change the clock, the content of one flip-flop goes into the next one flip-flop, and at each cycle the logical expression is computed and the outcome of logical expression is fed into the first flip-flop. So in this way we generate a binary periodic sequence which is known as PN sequence. If we have M flip-flop in the shift register and its initial state is known and we have feedback logic, then we can easily compute what will be the outcome of logical expression and what will be the output of PN sequence. PN sequence is mostly consist of ones and zeros which are represented by polar signaling. A good PN sequence is characterized by autocorrelation function which is similar to white noise. The autocorrelation function of PN sequence must be high at tau equals to 0 and low for other taus. The bit rate of PN sequence is known as chip rate and it is 10 times or more than the data bit rate. The chip rate is defined as 1 by T chip, and T chip is the duration of one bit in PN sequence. The smallest time increment in the sequences of a certain period or duration is T chip, and it is known as time chip. The total period consists of NC time chip. The chip rate decides the final transmission spectrum of the direct sequence spread spectrum signal. Several spreading code are used in practical spread spectrum system. Some of these are maximum sequence, gold code, Kasmi code, and Barker code. In case of maximum length sequence, the shift register consists of, if the shift register consists of L flip-flop, then the total number of sequence generated will be 2 raised to the power L minus 1. In maximum length sequence, we have only 2 modulo adder, and in this feedback shift register, the 0 state is not permissible because if we have only modulo 2 adders in the feedback circuit and the initial state of the flip-flops are 0, then at each clock pulse the outcome of logical expression will be 0 and the input to the feedback shift register will be 0 at each clock pulse, and we will get 0 at all the time when we change the clock pulse. So, in maximum length sequence, 0 state is not permissible. That's why the period generated by the maximum length sequence restrict to 2 raised to the power L minus 1. In this figure, we have shown a maximal length sequence generator which consists of different flip-flop, and the feedback circuit consists of a modulo 2 adder. In modulo 2 addition, we have such kind of operation like this way. If there are two input 0 A and B, and Y represents the output, in this case the modulo 2 adder will be 0 1 1 1 modulo 2 addition 1 equals to 0. So using these properties, we can easily perform the logical operation at each clock pulse and can decide what input will be fed into the first flip-flop. So this is the basic block diagram of PN sequence generator, which generates maximal length sequence. The number of ones in the complete sequence and number of zeros will differ by 1, which is one of the most important property of maximal length sequence. For example, if we have n equals to 8, then there will be 128 ones and 127 zeros in one complete sequence. The second property of PN sequence is its autocorrelation function, as it is shown in figure 4. As we can see from figure 4 that the autocorrelation function is binary valued. As we have told earlier that at tau equals to 0, it should be maximum, and other instant it should be near about 0. So in this figure we can easily see that at tau equals to 0, the value is maximum, but at other instants the value is very small. The autocorrelation function of M sequence is periodic in nature, and it assumes only two values, that is 1 and -1 by n, as it is shown in this figure. Now, as we have seen that how we can spread the bandwidth of the information, we have two types of spread spectrum system. One is known as averaging system and another is known as avoidance system. In averaging system, the interference reduction take place because the interference can be averaged over a large time interval, and an example of averaging system is direct sequence spread spectrum. While in avoidance system, as the name suggests, that it avoids the interference. In this system, the reduction of interference occurs because the signal is made to avoid interference for a large fraction of time, and its example is frequency hopping, time hopping, and chirping systems. Now we will see what is direct sequence spread spectrum. In direct sequence spread spectrum, we also expand the bandwidth of original signal, but the process is different. In direct sequence spread spectrum, each data bit is replaced with n bit using a spreading code, or we can say that each bit is assigned a code of n bits called chips. This chip rate is n times that of a bit rate. Whenever a user wants to send data using this direct sequence spread spectrum technique, each bit of the user data is multiplied by a secret code called a chipping code. This chipping code is nothing but the spreading code which is multiplied with the original message and transmitted. The receiver uses the same code to retrieve the original message. Here we have seen the generation of direct sequence spread spectrum. In this block diagram, we can see that here is the original signal and this is the chips generator or Basically, we are using here PN code for the spreading of original signal bandwidth. These two signals are multiplied and the resultant will be the spreaded signal. This is also reflected in this waveform. This is the original signal and the bit duration in this signal is TB, and this is our PN sequence spreading code, and in this spreading code the bit duration is TC, which is known as chip duration. When we multiply these two signals, the bit duration is chopped into small time increments, and we can easily see that in this TV duration we have certain small time increments which has a duration of Tc. So now this resultant signal, the bit duration is quite small, which reflects the spreading of bandwidth, because we know that there is an inverse relationship between time period and frequency. If time is small, then obviously frequency is large. So this figure ensures the spreading of signals. In this block diagram, we have plotted the direct sequence spread spectrum transmitter and receiver. As we can easily see that first we take the user data and multiply this data with the PN sequence. After this multiplication, we are getting the spread spectrum signal, and this spread spectrum signal is used to modulate a high frequency carrier, and after this modulation we transmit the desired signal. Usually in this modulation we use phase shift keying modulation, where we use two values of phase to reflect the information, 0 to reflect 0 and 180 degree to reflect a symbol 1. At the receiver side, we just perform the reverse operation of transmission. First we receive the signal and we demodulate it using demodulator. For example, if here we are using PSK modulator, then at receiver side we will use PSK demodulator, and after this demodulation we multiply the demodulated signal with the PN sequence which we have used at the transmitter side, and after multiplication of this PN sequence to the demodulated signal, we pass the resultant signal with the integrator. Integrator provides the DC values of the signal, and this DC value is compared with the threshold, where if the value is greater than 0, we decide that a symbol 1 was transmitted, and if the value is less than 0, our threshold, we decide in favor of 0. So using this process, we can generate the direct sequence spread spectrum and can demodulate the direct sequence spread spectrum. Now we will discuss about the second spread spectrum technique, which is frequency hop spread spectrum technique. When we talk about frequency hopping, hopping itself signify the jumping, and what entity is jumping? That entity is frequency. So in this spread spectrum modulation technique, the frequency is jumping from one value to another value. So in this modulation technique, we uses m different carrier frequency modulated by the source signal. At a particular instant, the signal modulate one carrier frequency, but at the next time, the signal modulates another carrier frequency. Although the modulation scheme uses one carrier frequency at a time, but m frequencies are used in long run. The bandwidth occupied by a source after spreading is much greater than the bandwidth of original signal generated by the source. The block diagram of frequency hop spread spectrum transmitter is shown in this figure. As we can see that we are using a PN sequence for the spreading of signal, and this PN sequence drive a frequency synthesizer. Frequency synthesizer generate different types of frequency, and after this generation of different frequency, the original signal and outcome of frequency synthesizer is applied to the modulator, and the outcome of modulator is the spreaded signal. We can explain the working of this transmitter with the help of these two tables. In these two tables, we have PN sequence, different combination of PN sequence, and corresponding to these sequence, what frequency the frequency synthesizer will generate is reflected in this portion. For example, when we have a combination of 000, the frequency synthesizer will generate a frequency of 200 kilohertz. When we have a combination of 011, the outcome of frequency synthesizer will be 500 kilohertz. Similarly, if we have the input 111, then frequency synthesizer will generate a frequency of 900 kilohertz. So, in this way, by changing the PN sequence, we can change the output of frequency synthesizer. For example, if M is 8 and K is 3, the pseudo random code generator will generate 8 different 3-bit pattern. These are mapped to 8 different frequencies in the frequency table, which is reflected in this table. The pattern for this station is 101, 111, 001, and these pattern is pseudo random and it is repeated by the sequence generator. The second k bit pattern, for example, selected is 111, which select a frequency of 900 kilohertz. If an intruder tries to intercept the transmitted signal, he or she can only access a small piece of data because she does not know the spreading sequence to quickly adapt herself to the next hop. This scheme has also an anti-jamming effect. A malicious sender may be able to send noise to jam the signal for hopping period, but not for the whole period of transmission. So, if at any instant some intruder can have knowledge of particular frequency, but we change, and when the intruder wants to jam that particular frequency, we have option to change our carrier frequency to next value. So, in this way, the frequency hop spread spectrum can save our transmitted desired signal. This is the block diagram of frequency hop transmitter, in which we are using different kind of modulation technique for long distance transmission, and in figure 10 we have shown the frequency hop spread spectrum technique utilizing the frequency shift keying modulation. The purpose of this additional modulation is to transmit the information to a long distance. This is the particular example in case of frequency hop. As we can see that for a bit sequence like 000, as we have seen earlier in the table, the carrier frequency is 200 hertz, 200 kilohertz. So, if we have some kind of data to transmit, for example, if we have 0 0 and we are using frequency shift keying modulation scheme, then for this 0 0 combination, the frequency I can assume f1, and the frequency synthesizer has a frequency of 200 kilohertz, then the resultant frequency hop displayed spectrum will be 200 kilohertz plus f1 kilohertz. Now, if we talk about there are two kind of frequency hop spread spectrum, slow and fast frequency hopping. Then if we talk about slow frequency hopping, then in slow frequency hopping, we can transmit multiple symbol during one frequency hop. So I am taking the example of slow frequency hopping. So the frequency synthesizer frequency is same, but we have another bit to transmit. For example, we have 0 1. So for 0 1 corresponding, the M array FSK modulator will generate a frequency of f2. Then for 0 1 symbol, the outcome of frequency hop spread spectrum will be 200 kilohertz plus f2, which is different from symbol 0 0. This example is demonstrated in this chart, in which we can see that we are using different frequencies for different combination of symbols as well as P N sequence. So this is the example of frequency hop spread spectrum. This is also reflected in this previous slide, how we can change the frequency. So these are the topics which we have to cover.